Variables can have a variety of different relationships. The first of those that we'll explore is called direct variation. And so this is where as one variable increases, the other increases or decreases at a constant rate. So it's a linear relationship. And so the equation is going to fall in the format of just y equals k times x, where k is this constant of variation. If it's positive, then our graph is going to be going up if we were to graph the relationship. If k is negative, it's going to be going down if we were to graph it. And so long as the x has no exponent on it, then it'll be a linear graph. Notice also that we are passing through the origin because there's no b value. If we were thinking of this as a y equals mx plus b, for direct variation, we're always going to have 0 as the y-intercept. So in the examples that we see in front of us, the first thing that needs to be openly stated is the type of relationship between the variables. So here we see y varies directly as x. We are explicitly being told that the variation is direct, so that means we can start with y equals k times x. So then we're given some information about the two variables so that we can determine what is the constant of variation for this particular example. And so in this case, it says that when x is 12, y is 8. So I'm just going to substitute 8 for y, and then I'm going to plug in 12 for x. And now I need to solve for k. I need to know what that constant of variation is. So if I divide both sides by 12, I get k equals 8/12, which reduces to 2/3. So there's my constant of variation, and so now I'm ready to write my mathematical model for this particular problem. And so all that is my y equals kx equation with just the constant of variation plugged in. So my model equation for this one is y equals 2/3 x. So that's my model. And then I can use that to find one of the variables when I know the other for the duration of this question. So in this case here, we're told that we want to find x when y is 18. So I'm just going to plug in 18 in place of y equals 2/3 times x, and then I'm just going to solve for x. So normally we would divide by whatever's multiplying the x, but since it's a fraction, I'll multiply both sides by the reciprocal. So we just have a little reducing to do, replace that 18 with a 9, and so we get x equals, that was a 3 here, so 3 times 9 is 27. So we found the model by using the relationship between the variables as being direct, and then knowing one set of values for which this relationship is valid. Use that to find the constant of variation. That gives us our model equation, which we can then use to solve for another missing value. So the second example is very much the same thing. So we can see again, we have to be told explicitly what the relationship with the variables is. So it says y varies directly as x. So I can start off with y equals k times x. I can then use the given information about the variables. So when x is 10, y is -4. So let's use a 10 there instead of a 4. Let's try that. And so now we just divide both sides by 10 to figure out what k is. So we get -2/5. So my model is then just with the k plugged in. So I get y equals -2/5 times x. So there's my model equation right here. And so now I can use it to solve the remaining outstanding part of the problem. So we want to find y when x is -40. So we can just say y equals -2/5 times 40 over 1. So then I can reduce, the 5 goes, the 40 becomes an 8. So we get -16 as our answer for y. In our third example, we just have a little bit more work to unpack, but it's still going to be a direct variation relationship. So in physics, we have this Hooke's law, which states that the distance that a spring is stretched or compressed from its natural resting length varies directly as the force that's applied to it. So we have distance varies directly with force. So they have to tell us that the nature of that relationship. So just like we were told up here that y varied directly with x, we can write that the force varies directly with the distance. And I could have reversed those variables. I could have done the same thing on the above questions, written it as x equals k times y in both cases. The only difference to the outcome under any of these circumstances would be that the value of k would be its reciprocal. So here, if we wrote x equals k times y, then k would have turned out to be 3/2. Here, it would have turned out to be -5/2. So in this case, for direct variation, it does not matter what order you put the variables. The only difference is your k value will be the reciprocal, but everything else will work out just fine. So continuing with this one, if we write it in this F equals K times D format, which is kind of standard for this type of question, so we've got a force of 100 newtons stretches the spring 0.25 meters. I'm going to plug those values in to figure out what K is. So I've got 100 for the force equals K times, and then I've got 0.25 for the distance. So if I divide both sides by 0.25, I can push buttons on my calculator, or if we do it in our head, we'll see that we get K is equal to 400. So now my model equation in this case is F equals 400 times D. So for this particular spring, the K value is 400. For some different spring that either has more tension or less, that K value would be different. But going forward here, now we have a new force of 80 newtons. So I'm going to plug that in for F, and then I just need to solve for the distance D. So we divide both sides by 400, and since our original problem gave a distance in a decimal value, we'll go ahead and divide that out. So we get D equals 0.20 meters. Just want to make sure that we label our final answer. So again, our model equation is when we've got K plugged in, but the other two variables are still present, and then we just use that model equation to solve for the missing piece of information. As mentioned briefly earlier, we can also have direct variation with an exponent on one of the variables, like x to the n, or a square root, or a cube root, or something like that. So we still have a direct variation relationship, it just happens to not be linear. So in the example we see in front of us, we have the temperature of a pot on a stove varies directly, so we've got that, with the square root of the amount of time that it's been heated. So we've got the temperature varies directly with the square root of the amount of time. So we can go ahead and say T equals K times the square root of the amount of time. So I'm living dangerously here with capital T and lowercase t as my variables, but hopefully we can keep those straight. So it says after 4 minutes, the pot has a temperature of 120 degrees. So I can plug in 120 for the temperature equals K times the square root of 4, which is 2. If we divide both sides by 2, we get K equals 60. So we have our K value. So now our model equation is going to be T equals 60 times the square root of the time. So there's our model. And so now we want to know how hot will the water be after 9 minutes. So I'm just going to replace T, the lowercase t, with 9. So we get T equals 60. Try that again. 60 times the square root of 9. So 60 times 3. So our temperature is going to be 180 degrees.